All right, so good afternoon, everyone. This is a fairly long tale that I don't have a lot of time for, so let's just go right into it. Next slide, please. So the question I have here, this is geology, but this is really geology about water. And it has to do with how water can be retained, besides in the permanently shallow regions. Next slide, please. So, of course, to have water exposed to vacuum and looking at the sky and to survive for any sort of geologic time, it has to be very cold. But what if you don't want it to be very cold? Can you have water in regolith? There is actually evidence from the LIND, the Lunar Exploration Neutron Detector, which is on LRO, that there is hydration, thus presumably water, at latitudes beyond just where the PSRs are. And we will get into that in some detail. So in a regolith, the water will always, if water's in the regolith is ice, unless it's like encapsulated in glass spheres or something, it'll always escape. But the question is, how long will that escape cost? And so we're going to estimate diffusive lifetimes to a depth of about 1 meter using the diffusion models of Shorgoffer and Taylor, and so on. So let's go on. Next slide, please. First off, we need a temperature model. We've been working on this for a while. We've been using the extending the temperature model of Vasavada to a 3-layer model because we want to go down into the core, into the crust. We actually fit one parameter, which is an effective albedo, infrared albedo, to the Apollo 15-17 ALSEP data, which I think gives us a little better performance in Vasavada. But temperatures in this model at about 1 meter below the surface range from 260 Kelvin at the equator down to 140 Kelvin at 85 degrees north. Next slide, please. So this is just a slide of this, and you see that at low latitudes, say 45 or even 58, where Clavius crater is, the subsurface is pretty warm. You go down 1 meter, that's below the sun-induced heating cooling cycle over a month. You're pretty insulated from that, but it's still fairly warm because you're still feeling that solar radiation. You have to go way far down, way far up in latitude to really be cold down there. Next slide, please. And that was for a spherically symmetric model. It was only a symmetric model. I don't know why that's upside down, doesn't matter. This is the resonance time, and you see the resonance times really increase. This is how long a molecule of water will stay where it is. At 250 K, it's like way less than a second. At 100 K, it's starting to be like a few thousand years. And now that's for one molecule, but that still means, next slide, please, that you will lose 1 meter of water in say at 85 degrees north or south, you'll lose 1 meter of water if it's exposed to the sky in about 1 million years. And so you cannot have the upper meter of regolith contain water. It just won't work if that water is exposed to the sky. And that kind of suggests that ideas that, well, what you're seeing is you have shaded regions, and so you have boulders or whatever that are shading some regions, and so you have water that's exposed, and now it's still going to be too warm. Next slide, please. So let's look at hydration data. So this is from the LIND, from Livingston. Next slide, please. This is the hydration data as a function of latitude. This red is the red crosses or red pluses are northern hemisphere, blue crosses are southern hemisphere, the green is squares of the difference. You see that the northern hemisphere always has more water, more hydration at least, than the southern hemisphere, which is kind of interesting because the southern hemisphere is thought to have more area in PSRs. And so if this was just a PSR effect, you would expect it to be different. And notice that it's kind of flat up to about 75, 77 latitude, something like that. And then it starts increasing more or less linear latitude. Next slide, please. So I converted this to the on the left is the same data, the weight percent. Notice that 0.1 weight percent is about 1 kilogram per cubic meter of water in regolith. I converted it to survival times. So this is using that diffusive model, using the diffusive lifetime model, and you can see that up above about what's effectively 75 latitude, you start getting to million-year lifetimes. 100 million year lifetime is about 80 degrees latitude, either north or south. Billion-year lifetimes is about 84 so latitude, 83 latitude. Now, if you're following lunar dynamics, which actually hasn't entered in too much in this meeting so far, we think that there was a Cassini state transition at some time in the past, and the people who really are involved in this, like Bruce Bills, are arguing about, well, how long ago that was, but say 1 billion, 2 billion, 3 billion, something like that. As the moon receded in its orbit away from the Earth, you went through this Cassini state transition, and so the moon went from one state to another. In the middle of that, it wasn't in a state. And when it wasn't in a state, the obliquity was not constrained, and the obliquity might have gone up to some large number, 50 degrees, 70 degrees. And what that means is, during that period, which would have certainly lasted a few million years, maybe longer, the polar regions were baked out. And so any water in the top kilogram or top kilometer or so of the moon at the polar regions would not survive that. So you could have deep water that did, but shallow water would not. And a kilometer's not that shallow. Next slide, please. So, and an interesting thing too is that heat pulse from 1 billion years ago might be still making its way down into the lunar interior. You might have a fossil heat pulse down about somewhere between 10 and 20 kilometers below the surface, still going down. And so you might have not a monostatically increasing temperature. So we had a client who asked us to find high latitude landing zones, and I was trying to find interesting land in the northern hemisphere. And so I found some interesting things there. Next slide, please. And what I found is that there are signs of tectonic activity up in northern hemisphere. There's signs of moonquakes. There's signs. I mean, there's not up signs. There's observation of moonquakes. There is wrinkle ridges, but also, next slide, please. There are other things, and I'm going to look at one of these, what I regard right now as the best one, in some detail. So this is Philolos crater. You see that there's a flat lava plain there on the eastern side of it. I have an interesting area, but the whole flat lava plain is actually not flat. Next slide, please. It's full of stuff. And what kind of stuff? Well, there's two sets of real patterns, at least. There's an east-west real pattern and a north-south real pattern, which intersect at places. I don't know what that means about subsurface lava flows. There's all kinds of extrusions. There's also apparent skylights. Now, up at this high latitude, it's hard to tell if a skylight's really a skylight because you never see down into it. It's always shadowed, or what looks like skylights. And then there's things like, well, this mesa dome is about 1 kilometer across. Next slide, thank you. There are these domes here, which are I call the line domes because they seem to be, next slide, please. And this, I call this one the Stegosaurus dome because it actually seems to have plates coming up, which reminded us a little bit of Stegosaurus. The fact that this has boulders on it says this is geologically recent. This looks like something is pushing up from below. It doesn't really look like a wrinkle ridge, however. It doesn't look like a compressional feature. It looks like there's something going on. And what I have to wonder is, given where it is, given that this is near an Alsep moonquake area, so presumably it is shaking, it could be doing it now, could this be like a water diaper or something like that, where water is being forced up from below? So that's the story so far, and I will just leave it at that. Thank you.